Alright, hello, my name's Ford Hash. This is my final project for graphics with Dr. Poor, and my project was basically to try and do some ocean water simulation, as you can see here. Basically do the simulation of the water, moving water, and level of detail that moves with you as you move across the scene, along with a skybox and also some extra graphical enhancements like foam and what we'll get to later. So that's the goal. And as I started out this project, basically my inspiration came from when I went to SIGGRAPH over the summer in LA. So me and my mother went to go to SIGGRAPH, and I saw a bunch of interesting presentations and cutting edge graphic stuff and stuff like that, and I saw this ocean simulation crest. It's like a Unity framework for ocean simulation. So I was like watching this presentation, and I thought that some of the stuff they're doing is really cool. And obviously I didn't get to implement like everything they did, but I thought some of it was really cool, and I wanted to try and at least do part of it, you know. So what they ended up implementing is called CD clip maps, and they explain in their presentation like why it's better than the previous approaches, such as CD LOD, which other people had done in the past. And I basically ended up implementing like half of CD clip maps. I used taxi cab distance, and I did skirt geometry and shape connection, and we'll get to stuff like that later. So and then I was looking around. They reference also a SIGGRAPH paper done by a guy named Tessendorf. Let me pull it up. Guy named Jerry Tessendorf in like 2001, I think, and he goes through this long paper, really technical paper, describing ocean rendering techniques and a bunch of different stuff. Like, it's not just the geometry; it's like everything to do with ocean rendering. But I was mostly just using it for the geometry. So we have. Starting here, he goes through algorithms to generate like ocean wave geometry. And as I was reading through this paper, it's very technical, like I said, and so some of the stuff just kind of went straight over my head, and I didn't really know where to start with actually implementing it in C++ and OpenGL. So I searched for maybe someone who had like a explanation, and I found this guy, Keith Lance. He basically goes through a tutorial on how to implement Tessendorf's paper, and it includes like all the technical help, like explanations of the algorithms and also the actual code itself, for his implementation of it. So I basically used his implementation of it as a framework to build my stuff off of, because Tessendorf's paper is so technical, you know, I couldn't really get into it that easily. So now I'll explain some of my process. I'll try to keep it high level, and maybe we can look at some of the code too. So my first lowest level that I wanted to achieve was generate a static mesh. This is before I even researched it. So as I found, generating a static ocean geometry mesh, sorry, my mic's really loud. Generating a static ocean mesh is actually not really useful. It's not really a useful goal in this case because the implementation is all dependent on time. So like generating a single frame, basically you have to do the whole thing and then give it a single time to generate a static mesh. So it basically just starts with level 2, which is generating the simple I say simple, it's not that simple. Moving waves using Tessendorf's algorithm, or the algorithm that he goes over. And so I started out using what's known as Gerstner waves. He explains it at the beginning of his ocean wave algorithms. Basically, it's an approximate solution to fluid dynamic equations, very old. Started out with that. It's interesting, but it's not that useful because he gets into the actual statistical wave models and Fourier transforms. So that's when it started getting way over my head. But that is the model that I used because it's more accurate and it's based on statistical models. And so what's cool about it too, the statistical wave model that he explains, is that it's tileable in space. So it generates like a tile basically, and it's tileable in space. So you can put them beside each other and it'll be seamless basically. And it's also periodic in time. So you can generate basically a period of time and it'll basically seamlessly like restart, So I started out with Lance's implementation. So let's see, this is the second page. So Lance gives, this technical introduction and then his implementation. I use this as a framework basically. I ended up changing it quite a bit because even though he published this in 2011, he still used shaders and stuff that we haven't learned in the class. So I had to basically make it not as good because I cut out all the shader stuff and all the optimizations basically, besides the fast Fourier transforms, which is the main optimization of the algorithm. And I used his implementation for the fast Fourier transform like mathematics. I just straight used his implementation. I didn't try and mess with that. But his actual like graphics implementation, I changed quite a bit. So yeah, see, he goes into like shaders and stuff, and I didn't use any shaders because we didn't learn OpenGL with shaders. So basically downsized it, and his implementation also only handles rendering a single tile, and obviously I had to change that quite a bit because I wanted to do level of detail, also moving around the scene, stuff like that. So we'll get into that a little bit later. So then level 3 was my idea for level of detail, which I saw in this presentation at SIGGRAPH. And I did not implement their implementation because theirs is quite technical as well. Like their tile transitions, geometry transitions it's pretty cool. Like it's a smooth transition. I didn't quite go into that depth, but I do have the level of detail. As you can see, I'll give it a bird's eye view and we can see the wireframe. So I have this is the level 1 and level 2 and level 3. And basically my implementation starts in the very center and does like a spiral loop basically, and then until it gets to the outermost of the inner level, and then it transitions to the next level and then goes around in a spiral. So we can show the code for that real quick. So this is in the draw method of the waves class, and you can see this is the loop that actually does all that spiral drawing and the law transitions as well. So then, before I get on with too much of what I did with level of detail, I want to mention my level 4, which was foam, and how it didn't really work out. So I'll enable it real quick and you can see if it shows up. Basically, what I thought it was going to look like, there it is. What I thought it was going to look like did not turn out how it actually looks like. The papers that I saw, like this paper mentions foam, like here it has the foam here. they do like, it's like the Jacobian determinant calculations inside their shaders, and I had no idea what that means basically, and I couldn't even figure it out with research. And then another paper I saw used like a squash, is some algorithm based on the displacement as well, and so I ended up using like straight if the displacement was over a certain amount, the displacement from the original grid basically. All these points start out as a flat grid, and then they get displacements through the fast Fourier transforms, and that's what actually generates the waves themselves. So if the displacement is over a certain amount and is above the actual sea level, then it like basically says it's like a particularly high peak, and it gives it some like white coloring, but obviously it doesn't really look that great. It doesn't look like foam at all. So that was one of the drawbacks of my highest level that I wanted to try and achieve. But to try and replace it, I ended up doing some other cool stuff with level of detail. So I wanted to show that off real quick. So if we go back to a bird's eye view and turn on the wireframe, we can see it without the fill-in with the wireframe. And so basically what I ended up doing was to expand on level of detail and to try and replace the level 4 that I had, top level that I had, was at first my levels were not stitched together. That's what this paper was talking about when it was talking about shape connection. So basically, let me go down a little bit and decrease the levels so it's easier to look at. Oops. Yeah. So now we have fewer layers, is what I call it. It's like the number of sections on the same level of detail that it goes out before it transitions to the next level. So this is the smallest level down here. So basically when it transitions to the next level, the closest tiles are not inherently by the algorithm connected to the previous level. So for example, like this vertex right here wouldn't be connected if these were just, if this tile in particular was just drawn like your regular square, like these two triangles, and then that vertex wouldn't be connected to anything, so it would show up as like cracks in the actual geometry as you see it. So it wouldn't look very good. It would have a bunch of white cracks basically. And so I solved this with this shape, which breaks the tile up into two, instead of two, it breaks it up into 3 triangles and connects that vertex to the other 2 in the square. And that makes it connect seamlessly basically. And then I also did skirt geometry, as this mentions, after that, which is cool because it lets you actually like kind of see out into the horizon and not have like a break where you can see like dropping down into the skybox. So we can see that kind of here. See, like this out here is the skirt geometry. It's not like your regular squares right here. It's like extends all the way to 0, and my like world max x and z values. So that's skirt geometry. And I also tried to implement as much customizability here as I could. So as I already mentioned before, you can change the number of levels of detail, and then you can change the layers, which is like how big the levels are basically, how detailed it is, and you can change the tile size. That's how big the tiles themselves are, and then you can change the detail, which is how small, like the smallest unit that the smallest level of detail actually shows. So if I change that to 9, for example, I get like it starts to get really slow, obviously, because this is all done on the CPU. So that was something I did not get to, which this. Their implementation uses minimal CPU. Mine uses entirely CPU because there's no shaders. So Yeah, so if you go over 8, it starts to get really slow because it's basically calculating the smallest level for the entire tile, and then only drawing the vertices that it calculates it needs to for the level of detail. So it's still actually doing the calculations for all of them. So yeah, after 8, it starts to get pretty slow. You can change the amplitude, which is like the height of the waves, basically. So I tried to make it not go higher than this because it starts to get pretty freaky. Yeah, and pretty slow here too. So yeah, it starts to get pretty crazy if you go over a very small value. So let me put it back. Yeah, my presets are pretty good values for actually viewing it. And then you can change the wind direction. So all of these right here, these 4 or these 5 completely reset the shape. So these do that, and then these 2 don't reset it because they don't need to. But the wind direction basically is used in the algorithm to calculate like which direction the waves are going towards. And then you can change all the camera positions and stuff, and you can change the wave color. So change this. You know, that's like a really bright blue, and you can change it to like some murky green. You can change the light color. So, or that's the transparency. Sorry. So yeah, I also have like, you can make it transparent. It doesn't look that great because that's also one of the drawbacks of my implementation, is it doesn't really handle transparency that well. It looks fine, but you know, like you can see the skybox and everything. But, so let's reset that, and then you can change the light color. So that's pretty cool. And then you can change the time. So that's basically the position of the sun, or the light, the global light over it. So like 12 is like directly above it, and then you start to see some like specular reflections if it gets to like a certain angle, which makes it look pretty nice, like a little sparkly. And then you can change the compass direction of the sun, which is basically like turning the sun around it. And you have to get that right too to see the specular reflections. So, and then so I went over direction of the light, time of day, the colors. Oh yeah, I also have a pause button, so you can pause it if you want to like go into some detail. You can change all of this stuff as it's paused, change the camera location as it's paused too, and everything. So yeah, so and then I need to. So that's basically the. Oh yeah, one more thing. Also, I almost forgot. Very cool thing that I ended up implementing was, at first I set basically the center of detail to be right below the camera point, like most people do it. So it's like the closer stuff to you actually is more detailed. That's the whole point of level of detail. But then it got to the point where you can't really actually see, like if you're looking out over the horizon, right? So you're looking out this way and you can't really see the stuff closest to you, so you don't really get use for that detail that you're using. So what I did was actually use a raycast, which is done here. I basically cast the look vector into the Y plane, and at the intersection I use that as my center of detail. So as you can see, if I move the camera down, the detail moves with like my sight position on the water. So if I move it out, see it kind of moves out. Let me show that just the wireframe, it'd be easier to see. So see, you can see the center of detail moving with it, and it's farther out. So I thought that was a pretty cool implementation detail that kind of extends the project just a little bit. And it basically makes it more detailed at the point where it thinks you're gonna be focused on. Like I'm kind of focused on here. I'm not really focused down here too much. So it makes it more detailed where you're looking, which is pretty cool. And then I'm just going to address some of the limitations that I had in this project. So obviously we went over the foam. Doesn't look great, but I think that's mostly just from not using shaders and getting the extra power that brings. Detail, like I said, it's all done on the CPU, so as you get more detailed, it starts to slow down a lot. Yeah. So just leave it about 8. And then Z fighting, you can kind of see at the peaks of these sometimes. A little Z fighting going on, which is like it's just something that comes with my implementation where it goes like spiral. The spiraling is actually pretty good for transparency because it renders stuff closer to you later. So if I bring my eye point down a little bit, like if you have it set to be transparent, it kind of helps it, like my implementation. Like you can see some of the waves sometimes you can see through them pretty nicely, which wouldn't work if you render them the opposite direction. But the Z fighting sometimes happens, like you can see on the peaks. Yeah, let's see over here. Like Z fighting happens just because of the direction I'm drawing it, basically. And I didn't attempt to address that really at all. And then the height issues. So you have to keep your eye point pretty close to the actual surface in order to get a good actual image. If you bring the eye point up, you can see what I mean. So see how it's casting the ray here, so it thinks I'm gonna want the most detail here, and then this obviously doesn't look good, but it does let you see that the tiling. So basically what the algorithm does is it calculates everything within a single tile, and then it doesn't have to do any more calculations, and it can just repeat the tile at different levels of detail. But yeah, it becomes really apparent as the Y value increases. So I didn't attempt to address that. Obviously it would make it really slow if I tried to do a lot of detail as the Y value increases. So got to keep it pretty low, and it looks pretty nice from here. Skybox, I basically just took Keith Lance, that guy that whose implementation I followed closely, has another tutorial on skyboxes. I didn't use the tutorial at all. I just used the picture because his tutorial uses also features of OpenGL that we did not get to use. But if we look up real quick, see the skybox. That's another limitation, was these corners. I could not figure out how to get that to go away. Yeah, there's the sun. Sun doesn't move because this is skybox. It's just static textures. But if we go up, we can travel to the edge. So there's the edge. Yep. So that's about it for my project. Hope you found it interesting. If you want to do a lot more research into this, definitely check out the Tessendorf paper. It was very interesting as a whole. There's a lot more stuff to get into that I did not even scrape the surface of. And also this presentation on Crest, which you can use in Unity. It's all open source, so you can use that if you're doing a Unity project, and it's really, really cool. They also go into a lot more stuff that I didn't get into, like depth peeling, stuff like that. Like it's like refraction and transparency and stuff. It's really cool stuff. So hope you enjoyed, and that's it. See ya.